Good evening, everyone. We are in the week 10 problem solving session of the course, Digital Control in Switch Mode Power Converters and FPGA-based Prototyping. Week 10 is about steps for FPGA prototyping of digital voltage mode control and current mode control. Let me share my screen. Is my screen visible?
Yes, sir, visible.
Okay. So we are in the week 10. Week 10 is about steps for FPGA prototyping of digital voltage mode control and current mode control. So whatever we had learned in the previous week, which is week 8, we had learned about Verilog implementation of voltage mode control as well as current mode control. And in week 9, we had seen some introduction to microcontrollers, which is again just an introduction part. We have not shown any implementation of the digital control. That will be beyond the scope of this course, but you are always free to explore different microcontrollers and you can implement the same. Only the platform will be different, but logic is same, so you can implement it using any platform, FPGA or microcontroller. So before we go into week 10, Banerjee has asked one question. So let me clarify that part. So I'm considering a buck converter. So buck converter. So there is an ESR and a capacitor. So there is a resistor, high resistor. So I'm representing high. So the current is low. My screen is, you can see my screen, right? Hello. Hello.
See, your annotations. Yes, sir, it is visible.
Okay. So R low. So what I'm doing is initially high resistance is connected, which means less current is flowing. Now I am connecting a lesser resistance in parallel and I'll close the switch. So it is a less resistance. Say we are maintaining the output voltage. So voltage is fixed, less resistance is connected. So there is a step in the I naught. So say this is I low to I high. So there is some load connected here, and the load is demanding high current. So initially it was demanding low current. Now it is demanding high current. So say this is that I naught, complete I naught, which is summation of these two currents. And here it has IL, and this is VC, and this is inductor, and this is RC. So we all know that inductor current cannot change rapidly. It has that inertia and it cannot change the inductor current rapidly because from the dynamics of the inductor, we know V is equal to LdI by dt, and inductor current cannot change rapidly. There cannot be a step function in the inductor current. So whatever this I naught that the load is demanding, IL cannot provide because it needs some time to increase its value, and it is a continuous function and it has got some dynamics, and according to it, it will take some time. So IL will take some time. So who will provide that inductor, like this current? If you see, KCL has to be followed, right? So say this is IC in the downward direction. So IL is equals to IC plus I naught. So if IL is not able to provide, so this current will be drawn from the capacitor. So this capacitor will provide that current, and because of this, because as this current is being supplied by this capacitor, so this extra current that this is delivering there will be a voltage drop across this RC. So if you see the voltage profile, I'm considering very less ripple. So at this instant, there will be a step down function because this RC, because this current, this this load current, that step that is being provided by the capacitor. So instantaneously there will be this current that this capacitor is providing, and there will be a drop across this RC, which will be reflected in this V naught curve. So there will be this drop, and then it will slowly, now inductor current will slowly try to charge the capacitor. So instantaneously at that instant, the load is demanding high current, which inductor is not capable enough to give it at that moment. So capacitor has given, because of which there is a voltage drop. And now the capacitor will recover. How this will recover? The inductor current will, so inductor current is like this, and it will keep on charging to that new value. So And so the V naught is something like this. So V naught at that instant, V naught has the capacitor has provided the current. So output current has been reached, but we are running it in a closed loop. Now V naught has come down, and also the capacitor has to be charged because the voltage has come down. So in the meantime, inductor, the closed loop will ensure this. The closed loop will ensure that inductor will be ramped up so that now again the IL will be equal to this I high. So the average should be, because inductor has to supply, the capacitor will never supply, but as inductor is not able to supply at that instant, capacitor has provided. Now this voltage drop, whatever that it got discharged, it will be again charged. Now inductor will be slowly ramping up the current. Now inductor current has increased and voltage is also become V naught. And because of this reason, there will be this drop. Is that clear, Banerjee?
Sir, up to here it is clear. Sir, like why R drop to control, sir? Why adapt to R drop the control is used?
Why?
By using R drop, there is a block in
This.
that closed loop implementation.
Uh-huh.
Yes, sir. Some R drop block is included and it is subtracted from the V reference.
Yes, yes.
In the
Okay.
lecture, sir is saying that to where the V naught is fallen, at that point he is maintaining the reference.
I'm not able to understand. Are you talking about that output capacitor has a resistor divider here? Are you talking about this?
No, sir, no, sir. Like, am I able to annotate on the same, sir?
No, I don't think you have that authority. So someone has mentioned, okay. I don't know. I don't know whether you will have this control on.
Okay. Sir, like what happened in the lecture is, the reason the block is like this. There are feedbacks and the feed forward are there. In addition to that, output voltage is taken and there is a block name as R drop and the reference voltage itself it is changing, sir.
Okay. I'm not able to exactly.
V reference dash is changed. V reference is now changed to V reference dash and it is equal to V reference minus some R drop.
So, like, did you see any this kind of diagram there?
No, no, sir. But
Okay,
so let
then
me snap one thing, sir. Am I able to? Are you able to see my annotation?
yes.
Okay. Sir, the reference itself has been changed and now the output voltage is like this, sir.
Okay. I got it. So yeah, I got it. So
Why? What is the problem if the voltage is placed like this? We are actually reaching our V naught.
I understood.
But
So
why
can you
we have
please
to change
erase your annotation so that I can continue?
Sure, sir. Sure. I will.
So there is this concept called as dynamic voltage scaling. So what happens is, say our V naught has a requirement, right? Say our V naught is 1 volt, and there is a requirement that it can stay from 0.9 volt to 1.1 volt. So the V naught should not go below 0.9 volt and it should not exceed 1.1 volt. So this is our requirement. So my V naught can stay in between these things. So what happens is whenever there is a step load, or V naught will happen and it will take some time to come back to that same voltage. So what they do is they will change the reference and they'll keep it somewhere here. So now it can quickly see here the settling time is this, right? So this is the settling time. And here it is reaching much faster, whatever this point. So now this new V naught dash and this V naught dash will be still in this region, right? So if my V naught dash is in this region, And if it is okay for that load, why to come back to the previous voltage? Instead, I can keep it as somewhat lesser voltage so that it will reach that particular voltage much faster. So I have changed the reference. Now it can quickly settle to that new voltage, and my requirement is met. Also, my transient response is improved because I'm deliberately reducing the voltage so that it does not have to come back to this voltage, which will take a lot of time. So the idea behind this is we are dynamically changing the voltage with respect to I0. So they will have this some gain, say G or minus R. So at particular load, say this at I naught equals to 0, the value is say V reference naught. So at I naught is equals to some I1, V reference, new V reference will be V reference naught minus R into I1. So this curve is again decided in such a way that our V reference will stay within this region, and this linear curve will be expanded over the light load condition to high load condition. So the main intention of this is to make sure that our voltage, output voltage requirement are met, so that it will lie within the range that it is supposed to be in. Also, I am dynamically changing my V0 so that say at this current, if I reduce the V reference, it will not take much time to come back to this voltage. It will be quickly coming back to this voltage. So it is to reduce the settling time and also to make sure that V0 is lying within this range. So they'll consider one straight line, and depending upon the load requirement, they'll dynamically change the V reference.
One more thing is, like, if the R drop is always there in the block,
No,
there is a
actually,
transient.
this is some resistance here. This is not load resistance. See, this is some say
Yes, sir.
RDBS. So that they will
Yes, sir.
decide accordingly.
Sir, like what I am thinking is, there will be always the V0 output voltage is less than the V reference what we have given.
No, that is, yeah, except at this condition, it will be V0 will be somewhat lesser because no, you cannot say that. We are changing the reference itself. V0 will be always at the V reference, but we are changing the V reference.
Sir, yes, sir, but let me one. It is like this. There is an R drop here. It is R drop. Okay. So here it is the V reference. Even though there is no transient, even though there is no transient, it is always subtracted from the V reference, right? Under steady state condition.
No, actually, one thing is I'm not sure whether you are talking about dynamic voltage scaling or not. So whatever I have understood from your question, I'm thinking you are talking about dynamic voltage scale. So I actually do not recall of such picture. So if it is dynamic voltage scaling, this is the concept. But if that is not dynamic voltage scaling, then it would be good if you ask, sir, because I do not recall that picture. So this concept is to scale the reference directly so that it will reach, like the transient will be faster. Yes.
One more question is
the undershoot of the output voltage. Sir, this capacitance discharge will happen up to the peak minimum value, right? Once the output voltage starts to rise after the minimum value, which means inductor has started to charge the battery.
Like after this drop will be instantaneous. So inductor current is ramping up, but it will need some time depending upon how fast we have designed the controller and depending upon the bandwidth. But as the current like it needs that instantaneous current, so capacitor will provide that instantaneous current, and because of that there will be this instantaneous drop in the V0, and now capacitor will be trying to recharge, and inductor will try to give the charge to capacitor so that they can go to that new steady state.
Sir, Sir, actually, what I'm asking is, sir, here you said there is a step change on the output voltage.
No, step change in the output current, not voltage. Like this point.
No, this is. Yes, sir.
Okay.
Sir, can I write, please, sir?
Like
Sir, where I'm asking is, sir, from this point to here, sir. From this point to here.
Got it. Yeah.
Sir, at that point, between that region, actually, capacitor is still discharging, right?
Yes, the inductor is trying to charge and capacitor is discharging. And after this point, inductor has got some sufficient charge and it is trying to recharge capacitor.
Sir, what I'm asking is, sir, in this same region, the inductor is supplying directly the load, right?
Inductor
it is not charging the capacitor.
It is also charging the capacitor and it is trying to reach to this new inductor current value, which is the steady state.
Okay.
Because inductor is not sufficiently charged in this region, so it takes some time. So capacitor has given instantaneously, and capacitor has delivered that power, and inductor does not have that power to give it to capacitor either. So it takes some time for the inductor to charge, and till that point capacitor will still discharge. And at some point of time, when inductor is sufficiently charged from the input voltage, then it will deliver to the capacitor, and slowly it will give to the load as
well. Yeah, sir. That is up to this minimum value of the output voltage. That is this minimum peak point. Capacitor is still discharging, right?
Yes, capacitor is still discharging.
After this peak only, inductor is again charging the capacitor as well as supplying the load.
Yes. Okay. So if again, Banerjee, so if this is about dynamic voltage scaling, so dynamic voltage scaling, they'll change the reference itself. So that depends upon the load current. But if your question is somewhat different, then you kindly ask sir in the next NPTEL session, or you can put that picture and post it in that NPTEL forum, so we can see where, or you can mention that video lecture where sir has mentioned that, so we can better understand your question.
Okay, sir. Okay. Sir, one more thing is, like, what is the exact use of the signal conditioning board and FPGA?
Okay, I'll come to that point. So I have put a slide where I can better explain you. So you remind me when I come to that slide. Okay.
Okay.
So to summarize, week 9 we have discussed about the digital control implementation using microcontroller. So it is just a basic introduction about microcontroller. So initially we had discussed about STM32 and why we are going for STM32 G4X, this Nucleo board. And then first we have seen the overview of family of different STM microcontrollers. And then we have discussed how to select for the digital switch mode power supply. So this is digital switch mode power supplies, how to select that particular microcontroller. And we have also seen what are the software tool requirements and what are the softwares that are needed. And then we have discussed about GPIO toggling, how to write the code. And also I have shown you the live demonstration. Also, we have seen the gate pulse generation. And we have seen the dead time, but we have not discussed how to write the code because that is beyond the scope of this course. So we have just shown that how it is generating gate pulse and what is the dead time, all these things we have seen. And then we have gone to the LLC converter realization where they are using ST microcontroller for the digital control implementation. We have discussed about the plant, different types of modulator it has, and feedback management, and what are the kinds of protection that they are having, and how digital control provide advantage or the analog control, and other advantages of microcontroller and how it helps in having these protections. All these things we have discussed. And then we have went into the Texas Instruments microcontroller, which is C2000. We have seen what how many number of ADC comparators it has, different type of clock frequency, different type of family of microcontrollers of C2000, and what are the differences. All these things we have seen, and what are the software tools that TI offer, and what are necessary to dump the code into C2000 microcontroller. All these things we have seen, and we have solved a few problems. 2 problems we have solved. Now, coming into the week 10. So week 10, we'll be discussing about mainly three aspects. The first part is digital voltage mode control and current mode control results, hardware results. So sir will show the live demonstration of these things. So digital VMC as well as mixed signal current mode control. And in the second part, we'll discuss about voltage based chord control. So this is again variable frequency. So we'll discuss this aspect also. And in the last part, we'll talk about something called adaptive on time. So this is our summary, like outline of week 10. So just to summarize, first we'll discuss about the digital voltage mode control as well as mixed signal current mode control, and we'll see what are the stability issues and how to design the ramp compensation. And in the second part, we'll see about voltage-based constant on-time control, top-down design methodology, as well as Verilog HDL implementation and a few hardware results. And then Sir has briefly discussed about mixed signal constant on-time, off-time current mode control, and Sir has shown a comparative study, and Sir has also shown the experimental results. So we'll quickly go through the experimental results. And final topic is somewhat important, which is the peak current based adaptive on-time control, where adaptive on-time is used and what do they mean by adaptive on-time, how the on-time is being changed. So adaptive means it is being changed. And so what is its top-down design methodology? And Sir has discussed Verilog code, and it is somewhat incremental code to voltage based. So I'm not going into the Verilog code. So we'll directly go into the hardware results and we'll solve a few problems. So first we'll discuss about the hardware demonstration of digital voltage mode control as well as current mode control. This we have already discussed in week 9, I suppose. So week 9, we have discussed 3 parts. One is the digital voltage mode control. Sorry, I think week 8. This is week 10, week 9 is microcontroller, week 8. So then mixed signal current mode control and then digital PSL. So in this lecture, we'll discuss about these 2 hardware demonstration, how SAR is running the code and some aspects of those things. So coming to this point. So this is again our power stage. And this is the connector which either there will be this data exchange, and the top board is the signal conditioning board. Signal conditioning board. And the bottom board is there is a board at the bottom. So this is at the bottom, which is the FPGA, which is Spartan 6 FPGA. So Banerjee, what was your question?
Sir, what is the exact functioning of this signal conditioning board and this FPGA?
Okay. So whatever data, say, let us talk about voltage mode control. So voltage mode control, we are talking about, we are using FPGA because we want to implement the digital control. So when we are talking about digital control, everything should be digitized. So the V0 that we have is in continuous domain, and we need an ADC to convert into the digital domain. So digitize, we need in the bits form, right? So for this, we need this ADC. So that ADC is sitting on this signal conditioning board. So let me change the color to some blue color. So this is the ADC, and this is the DAC. And it is going, it is communicating with the FPGA, and these are the switches for load transient or reference transient or to close the loop. So we have the flexibility to design these switches, and these are ADC driver, DAC driver, and this is the comparative. So that's why we need the signal conditioning board, and FPGA is needed to implement our digital control logics. So whatever we had discussed, the digital control, we are implementing the digital control, all the digital blocks, comparator, SR flip-flop, digital comparator, SR flip-flop, and PID controller. All these things will come in this FPGA. So is that clear?
what is this comparator, and you are talking about another comparator in the FPGA board.
So if I have a analog comparator, it means the signals are analog. Say, let us say I'm comparing inductor current. So inductor, let me use a different color. So peak current mode control. So IL of T and I reference of T. So this is analog comparator because the inputs are in analog domain. Now let us move to the digital domain. Say we had a digital comparator in chord-based control also. So where V reference is plus, and so this is V reference of N, and this is V naught of N. So here input are in a digital domain. So it is a digital comparator, and this is analog.
Sir,
Yes.
have you completed, sir? This one?
Yes.
Sir, in this, initially we discussed that we have four resistors now, four capacitors at output of the buck or boost converter. Sir, initially it was said it is to reduce the ESR.
Yes.
Effective ESR will come down. Sir, here what is the and also it is said the higher more the capacitance value, ESR also will be high. They are proportional.
Like if you connect them in parallel, then effective ESR will be reduced.
No, sir. I'm talking about individual capacitor.
Yes.
Individual capacitor, the capacitance value is high, ESR also
will also be high.
Sir, in this combination for parallel, what is the value of ESR? Finally,
things.
you arrived, sir.
So one thing is like they'll never mention the ESR value of capacitor. So we have to we can never get the exact value of ESR because it is a parasitic. Inductor in datasheet you can get the RL value in the datasheet, but capacitor you cannot get. So we'll never get the exact value of ESR. It would be somewhat difficult. But we'll connect in parallel so that we can ensure that it is less.
Okay. Which means, sir, if suppose if I want if I want 40 microfarad capacitor the output, suppose in our design, can I put 410 microfarad in parallel?
Yes, that is up to you. Like again, I have mentioned there are two constraints, right? So the first constraint is the space. So you cannot put many capacitors. Again, it increases the space. If you're fine with that, then that is fine. And the other one is ESR. So if you increase number of capacitors, your ESR will reduce, space will increase. If you decrease the number of capacitors, your space will reduce, but ESR will be. So it is up to that person, like the designer, how many number of capacitors he wants to put.
So here all are for equal values, sir?
No. The bigger one is big value, smaller one is small value. So they have considered a combination of capacitors.
Okay. From that usual charge balance, we will arrive at the C value. From that C value, they are putting 4.
Like they'll never get that number of capacitors. So say their capacitance requirement is some 400 microfarad. So it is up to the designer choice how like they can consider 100 microfarad 4, or they can take 10 microfarad 10, then it becomes 100 microfarad, and 300 microfarad, then they can take 47 microfarad or 22 microfarad. So you have wide range of capacitance values that are available. So it is up to your choice how many number of capacitors you want to put and what type of like what is the value of the capacitance that you want to select. Okay. So there is again less than a minute. So if this meeting ends, kindly quickly join so we can continue our discussion.
So, sir, is there any?
Yeah.
Last question, sir. Is there any difference in ESR between the through-hole capacitor and this SMD?
Yes. Again, SMD has less area. So less area means again less path, so resist to path. And if you consider through hole, so that pads, exposed pads will have higher inductance effect, all those things. So that's why for high frequency we always go for SMD, because that exposed path is again parasitic, so we also don't want that. So this trace length also has some parasitic, less, but it will still have some finite parasitic.
So you mean, sir, you're saying then the SMD is of SMD?
Yeah.
Sir, this SMD has higher ESR, right, sir, compared to through hole
No,
of same value capacitance?
no, like, see, if the trace length is more, it will have higher impedance path. So SMD will have lesser parasitics compared to through hole.
Okay.
So that's why we always choose SMD, which has lesser parasitics compared to through hole. But if your application demands through hole, then you have to go through hole, and you should consider that additional parasitic also.
Sir, which way you will usually measure this ESR suppose in our lab, if you want to measure?
Like, it is difficult to measure because that is a parasitic. So like either the manufacturer has to give some information, else it would be very difficult to measure. And measuring ESR, it is like very difficult. For inductance, you can get some estimate from the datasheet as they mentioned, but for ESR, it is not like you'll not get any accurate value.
Okay, sir.
Okay. So first we'll discuss about the voltage mode control, as this part we have discussed in the previous week 8. I'll just quickly go through it. So this is the Verilog module, and the feedback is going to the analog to digital converter, which is giving ADC data 10-bit, and it needs FADC clock that is generated by this module, and it has Q trans switch, F clock main 100 megahertz clock, and it is giving 2 gate pulses, and also the Q load to give transient. Whether if you want to go from low load to high load or high load to low load, this is the pulse that controls that. So this is the overall structure of the setup. So this is the laptop which has the code inside it, and this code is being loaded into the FPGA, which is at the bottom side, and the top side we have signal conditioning board. This is the power stage, and this is the oscilloscope, and this is the power supply. So whatever power supply that is needed, input as well as auxiliary supply, it is giving supply to the board, and we have connected the probes here. And this one is the inductor current probe. So this is the current probe, and this is the voltage probe. So the top one is the voltage V0, and the bottom one is the inductor current. And this is the zoomed in picture. So this is a low transient response. As we can see, the inductor current is going from low value to high value, and then high value to low value. And this is the supply, power supply. So this is the overall structure of the digital voltage mode control, and Sir also has shown some live demonstration itself. So let us move into the other part, which is the mixed signal current mode control. As we have discussed, everything is similar to voltage mode control, except it has this additional part because the current loop is in analog. So this is the analog domain where current loop is in analog domain, and voltage loop is in digital domain. So we have the V feedback again going into the ADC. This entire part is similar as this entire part is same as voltage mode control. So this ADC giving 10-bit data, and then Q tran F clock Q comparator. So this Q comparator is coming from the comparator output, and if we talk about the output, so the DAC data is going to digital to analog converter, which is giving us I reference, which is being compared with the inductor sensed equivalent voltage, and the output is Q comparator. and we have this two gate pulses that are going to high side as well as low side switch, and then again this is for transient. The details of the Verilog code, the internal instantiation of different modules, and the Verilog code we had discussed in the week 8. So we are not going into the details. We'll see the demonstration of mixed signal current mode control. So again, it is the same. So the code is being written in the laptop, and it is being dumped into the FPGA using this quad USB to micro USB quad. And these are the results of load transient response of current mode control. And here we have this pen drive to save the details and save the picture of this result. So we can copy that into pen drive. So it will be saved in JPEG for JPG or BMP, any format that we can select. And again, see the top one is the signal conditioning board, SCB, and there is a board at the bottom, which is the FPGA board. And they're connected through this connector so that the data can be exchanged from FPGA to the main board and main board to FPGA signal conditioning board. As we have discussed, this is the pen drive. So the top waveform is again V0 and the bottom waveform is inductor current. So again, this is load transient. And this is the power supply giving the power. So the wires are connected to the input as well as auxiliary supply, and one current probe as well as voltage probe. So this is the voltage sensed voltage. So this here they're sensing V0, and here they're directly getting the inductor current. So before we go into the constant on time voltage based constant on time, so this we had discussed in week 2 or week 3 that for mixed signal peak current mode control, there is a constant on the duty ratio beyond which it will be unstable. So if you write this IL n+1 in terms of IL, you will get this equation, and the duty ratio is nothing but I reference n minus IL n by M1 dt. So this is because it is peak current mode control. So if you back substitute this in this equation and then put up the expression, we'll get this final expression. Now considering zero input dynamics, so for current loop stability, so we have considered zero input, which means there is a I reference perturb is 0. So it is a constant reference. So perturbation is 0 because I reference is constant. Then as if we are checking if we are giving a perturbation in initial state and checking whether it is stable or not. So if I reference perturb is 0, then we'll get IL perturb of n+1 is equals to minus M2 by M1 into IL n perturb. So now you apply Z transform. And then by applying Z transform, we will get Z is equals to minus M2 by M1. But we know for stability, mod Z is less than 1. So we'll be getting this expression mod M2 by M1, which means mod M2 by M1 is less than 1. So if you substitute, say this is a buck converter, we know M2 is V0 by L and M1 is V in minus V0 by L, and duty ratio is V0 by V. Substituting all those things, we'll get this result, which is duty ratio is less than 0.5. So if duty ratio is greater than 0.5, then it will have some stability issues, which we'll look into it. This topic we have discussed in week 2, so I'm not going that much detail. So you can refer to that lecture video if you have still some confusion. But this is just a basic math, so you'll be able to do. Now, if it has stability issues, how to overcome it? So there is something called ramp compensation. So we provide this ramp. So this green color is the ramp, which will be subtracted from that reference. And this green color waveform is compared with the inductor current. Again, if you write the expression, so ILN will be the same expression. And now duty ratio is nothing but I reference minus MC into DT into this point. So say this is X. Now duty ratio is X minus IL by DT. Sorry, X by M1T. And X is what? X is nothing but I reference minus MC into dt. So if you substitute this value of X in this expression and solve for duty ratio, you will be getting this expression. So duty ratio is I reference minus IL by M1 plus MC. So you got this expression. Now you substitute this duty ratio in this expression and then perturb it. So whatever we have done in the previous slide. Then you will be getting this expression. So if you go back, here we have minus M2 by M1, 1 plus M2 by M1. Here, as there is this compensating RAM with slope MC, we will be getting these expressions. Now again for current loop stability, we are keeping I reference to be constant. So I reference perturb is 0. And then we'll apply Z transform. And then find the equation. So Z will be again MC minus M2 by M1 plus MC. And we know that for stability, mod Z should be less than 1. So if you do this calculation, mod Z less than 1, we'll be getting this expression. So for a given M1 and M2, if we want to stabilize it, so if we are to stabilize it, then this is the condition. So MC.
Sir, why you are keeping like I reference perturb equal to 0?
So we are keeping constant reference and checking. So this is like a 0 input. So we are not giving any input. So we are giving 0 input and checking the stability. So if I reference
Like
perturb is 0.
disturbance in the input is
Yes,
0.
yes. So I reference perturb means I reference is constant, but disturbance is 0.
Okay, like I reference disturbance is 0, but with respect to which you are analyzing this, sir?
With respect to which means?
Like you are saying that disturbance is 0. Okay, that's fine. But IL with
IL.
But how will we get IL disturbance, sir?
See, like this is the system. Say this is some steady state. We are checking whether the system is stable or not by perturbing only IL. Say now I have perturbed IL. I want to see how that is. Say if the system is stable and say I reference is constant, there is some disturbance in IL. The system has to ensure that again it will come back to steady state, right? So that is what stable system means. And if it is unstable, if you give a perturbation, that will keep on expanding and it will never reach the steady state. So what we are doing is we are making I reference perturb 0 and we got one expression. And from this expression, if we perturb IL n, whether IL plus n plus 1 will be able to reach its initial state or not, that we can say that if mod Z is less than 1, then the system is stable. So we got the Z value and then we are applying it whether this condition is achieved or not. So in our previous condition, we got a condition that duty ratio should be less than 0.5, for which the system will be stable. So for peak current mode control, if we cross duty ratio greater than 0.5, it will be unstable. And for duty ratio greater than 0.5, we need some stability issue, which we have some stability issue. And for that stability issue, to tackle that stability issue, we have to give an external ramp compensation, and the slope of which is given by this expression.
Then what exactly my doubt is, like, what is the reason for the IL disturbance?
Like the stability,
Am I
like
clear?
how to see. I have given you one expression, and we are checking the stability, whether the system is stable or not. So what we are doing is we are considering its small signal model, and one way you can say we are checking the eigenvalues, the location of eigenvalues. What are the eigenvalue location, whether it is lying inside this mod Z less than 1 or not. So like this is that perturbed small signal model, and we are checking the eigenvalues of this one, whether they are lying inside that unit circle or not, and we are ensuring.
Yes, sir, that is okay. Like, what exactly my question is, like, we have IL and I reference in this expression.
Yes, yes.
You are saying that the disturbance in I reference is 0. That's fine.
It is
Then
constant.
you are considering you are saying that there will be a disturbance in the IL.
IL.
What is the factor that is affecting this disturbance, which is causing
Okay.
disturbance
The
in the IL?
reason for this. Okay, got it. Now I got your question. Say M1. So IL, this M1 is V in minus V naught by L, right? Say I am changing V in. Say V in, it got reduced. Say V in is changed. Say the slope has slightly increased. Now it hit here and then it is turned off, right? So now if you see at this instant, there is some disturbance, right? Previously it was here, now it is here. So there is some disturbance in the BN. Now we are checking whether it will be able to reach its steady state again or not, which means if a system is stable, it will be able to reach to its equilibrium point. But if it is unstable, it will be going far away. So the disturbance could be of anything. Say here, one such case is BN. So I'm considering there is some change in the weight. And this is one case study that Sir has shown in his lectures.
Okay, sir. Okay, it's clear now.
Okay. So for that reason, we got this expression, and this is the current loop stability of this, what do I say? Current loop stability when duty ratio is greater than 0.5. And this is for duty ratio less than 0.5. So now Sir has considered two case studies. One is for V in 2.2 and one is for V in 2. So Sir has reduced V in, so duty ratio will increase. So in the first case, this is without ramp compensation, and this is with ramp compensation. So Sir has seen that for this V in, the duty ratio is already less than 0.5. Sorry, greater than 0.5, and Sir is giving constant I reference. And as the duty ratio is more, it has some subharmonics and it has some issue. So how to tackle this issue? Sir has given a ramp compensation MC and the same reference. So the reference we are not changing, and Sir has reduced this input voltage from previously it was 2.5 or something, and now Sir has provided the ramp compensation, and now it is stable. So Sir has provided some MC ramp compensation, some value. And in the second case, Sir has reduced the V in 2.2 to V in 2 volts. Now it still has this subharmonics. And using the same MC, so whatever MC Sir has used here, Sir has used also in this case study. But for this duty ratio, it has some M1 and it has some M2 for this V in and V naught, and it has some M1 and it has some M2. So the MC value required to stabilize this system and the MC value required to stabilize this system are different. And when duty ratio increases, the MC value required to stabilize the system also increases. So whatever MC that we had used here, it was not sufficient enough to stabilize this system. It has improved somewhat, but it is still not sufficient to improve the system. So now if you want to improve the stability, then we have to use higher value of MC. So as the duty ratio increases, the MC value required to stabilize the system will also increase. So this part, is this clear?
Yeah, one more thing, like sir, subharmonics in the sense, the frequency component will be less than the switching frequency.
Yes. So this is the
yes, sir. Like what to consider, sir? I have to consider this as switching frequency or this one?
See, this is one cycle. From here to here, one cycle. From here to here, one cycle. So it has two cycles in this. But it has this frequency, which is a lesser frequency behavior, also high frequency behavior. So that's why here, if you see, it is in a multiple of switching frequency. Here it also has a fraction of switching frequency. So that's why we say it is subharmonics, because it is a fraction of switching frequency. Is that clear?
Sir, could you please repeat it once?
So let me draw it again. So the waveform was like this. So till this point, it is one switching cycle TSW, and till this point, it has one switching cycle TSW. So it has TSW time period. Also, this outer side, this also has time period T. So which means it has a less frequency harmonic component also, which is the reason of this peak. So this is fraction of switching frequency, and this is switching frequency. So it has
Like switching.
frequency component which are lesser than switching frequency. That's why we call it subharmonics.
Okay. Like switching frequency is included. The time period is inside and the outer switching is different.
Yes.
Like outer frequency.
Yes.
Okay.
As if
Sir,
T
like,
is 2S.
sir, you are saying that this is TSW, right?
Mm-hmm.
But the time period in the sense it is exact repetition of the waveform.
Mm-hmm.
Like within TSW, the switching, the waveform is not repeating, right?
Yes, yes. So that is because it has some stability issues, and that's why it is not coming to that same point. You are right. So that issue is because of this duty ratio. Because duty ratio is greater than 0.5, it is not coming because of that issue that we had seen over here, because the poles are not inside the unit circuit. So this issue is resulting in this kind of behavior. And in order to stabilize it so that it becomes like this, we have to give external ramp compensation. So that now it will be stabilized.
Sir,
Yes.
this without ramp compensation, this is sir, is this also called limit cycle oscillation?
No, like that is different. This is different. So like here, limit cycle oscillation means it will keep on oscillating, but here it is no such oscillation. It is at steady state, fixed value, but it has harmonics. Like it has switching frequency harmonics as well as harmonics lesser than switching frequency. Is that clear? So in the case of limit cycle oscillation, it will keep on oscillating around that reference. But here it is not happening. It is constant, but it has harmonics of switching frequency also less than switching frequency. That's why we are calling it subharmonics. Is that clear?
Yes, sir.
Okay. So we have, sir, Vn is equals to 2 volt after ramp compensation. System is unstable. Last figure. No, actually we are considering two such case studies. In one case, Vn is 2.2 volts. So here say duty ratio is D1. And in the other case, Vn is equals to 2 volts. So duty ratio is D2. So D2 is greater than D1. So we, as if we are increasing the duty ratio, so the subharmonic behavior is increased here. So the subharmonic behavior is increased. So whatever ramp compensation that was sufficient in this case to stabilize the system is still not sufficient in this case to stabilize, because the duty ratio has increased and the ramp requirement is dependent on M1 and M2. So for this case, the ramp requirement is more, but we have provided the same ramp and we have seen that it is still not sufficient to stabilize the system. So that is what we are showing from this figure. Is that clear?
Sir, can we compensate the ramp dynamically? Like,
yes, that is also possible, but your code has to include that.
Okay.
Whatever it has to calculate how much ramp compensation is needed, and it has to provide that ramp compensation.
Okay, sir.
Okay. So till this point, we have discussed about. Sorry, I think I have selected blank. So till this point, we have discussed about digital voltage mode control as well as mixed signal current mode control and the stability issues of mixed signal current mode control and the ramp compensation, some hardware results and experimental setup. But all these are fixed frequency, where the frequency is fixed. Now we'll go into the variable frequency control techniques, which we have already discussed. The architecture we have already discussed in week 2 and week 3. So now we'll directly go into the implementation. First design methodology and then Verilog HDL and then hardware results. So this is voltage based COT control. So here COT means constant on time. So on time is constant and off time is coming from the loop. So going into the architecture. So this is buck converter and the architecture of this is as follows. So we have V feedback, the same feedback that is there. Now it is going into ADC.
I have a doubt.
Yes.
Sir, in the constant on-time control, like will the load current will be also within the control?
Meaning I'm not able to follow.
Sir, like in the two-loop control, there will be both voltage and current will be monitored and controlled.
Yes.
Like in case of constant on-time and off-time, will the both will be controlled or not? That's my question.
Okay. So again, as similar to fixed frequency, variable frequency also has two such controls. One is the voltage based control and the other one is current mode control. So in voltage based, we only have information about voltage, and in current mode, we have both current as well as voltage, and one will be, so this is again mixed signal. So one will be in digital domain, one will be in current domain. So whatever we are discussing now, it is voltage based. So it has a single loop and it is a voltage loop and it will be digital. Is that clear?
Sir, this current mode control in the sense peak current on time, like
constant on time, constant
peak
off time, peak or valley.
Okay. That will, in that case, the both voltage and current will be controlled, right?
Yes. Like controlled in the sense we'll have two loops. So we can monitor both current as well as voltage. So we can put either a peak on current or a valley on current, as well as we'll regulate the voltage at that particular voltage.
Sir, can I say the current mode control will be like both load and input will be controlled?
Load and input in the sense? Input voltage is not
Current,
in our control. Output load, output
like,
current is also not in our control.
But both will be monitored.
Like we are, see, when we are talking about loop, we have the information about capacitor voltage as well as inductor current. So we are regulating it at a voltage V0, but how much current is being drawn, that depends upon the load. It can be 1 ampere, 10 ampere. At 1 ampere, we'll have the peak or valley corresponding to 1 ampere. At 2 ampere, we can have the corresponding voltage current reference for 2 ampere. Similarly for 10 ampere. But we are using both the inductor current as well as capacitor voltage in our control. So it has two loops. So we are having much degree of freedom because we are using both current as well as voltage in designing the control.
Sir, like current mode control has both good line regulation and load regulation. Can I say that?
Yes.
Whatever the case, the current mode control has both good line and voltage regulations, whereas voltage
as poor line
based
regulation.
has. Okay, sir. Thank you. That's the thing I want to know.
Okay. So this is being compared with that reference voltage, which is again digital. it is being compared, and then it is triggering that whatever constant on time module that we have, and we have discussed why we need minimum off time. So this is discussed in week number 2. That's why I'm not going into the details of this one. So this is already discussed in week 2. So if you still face any confusion, you can go through. So this is constant on time. Plus minimum off time. So this is this minimum off time block, and it also has a constant on time block, and then it has dead time, and it is giving the gate pulses. So the again front part is same. ADC data we have transient as well as clock 100 megahertz clock, and output it has PWM high, PWM low, and Q low. If you go into the details of this constant on-time voltage mode control, this is the main module. So main module has inputs as well as outputs. So we have clock ADC, outputs PWM high, PWM low, and input is ADC data. And here it has input, output, and wire and range declarations. So we'll not go into the details as it is. We have discussed for voltage mode and current mode control. And N timer, this is for constant on time. So this is constant on time, and this is minimum off time. So the on time and off time are defined. So T on constant on time is 100 clock cycles. So 100 clock cycles into T clock. So that is 10 nanosecond. So it will give how much? 1 microsecond maybe. And T off is 26 into T clock is 10 nanosecond. So 260 nanoseconds. So this is the on time, and this is T off means T off minimum. So that is set by sir in the code itself. Again, it is user choice. What is the constant on time that you want to fix and off time that you want to fix? Clock generator has already been discussed in voltage mode control. So we will not go into this. So we'll go into something called clock modulator and clock manager. Sir has discussed in detail in his lecture. So we'll not go into that much detail, but we'll just brush up the concepts quickly. So coming to the clock modulator. So clock modulator has enable, and N timer is for on time, and N minimum is for off time, and this is the 100 megahertz clock, and it has Q out as well as a Q finish. So the circuit is as shown over here. So first we'll discuss about these things. Enable generation of enable. This is again signal. Generating enable will come into this point in the upcoming slides, but for the time being, we'll not go into this. So it has 2 blocks. One is the constant on time, and the other one is the minimum off time. So the first block is for constant on time. Second block is for minimum off time. So whenever there is an enable, it will set, and Q will be 1. So there is no reset. Reset will be 0. So for this counter to start, say it has started counting. So N count will happen. You are able to follow, right? Hello.
Able to follow.
Okay. So N count will keep on increasing. Say I am, and whenever it touches N timer, then it will generate the reset signal. So it will. This is the N timer. So until this N timer, so whenever it touches N timer, it will give a reset pulse, right? So this reset pulse will make Q to 0. So until this point, Q is 1. And then now we have reset it. So this will reset the counter, and counter will be stopped at 0. Now when this reset is there, this reset will trigger this set pulse. When it is set, this counter will start counting. So now Q has become 0, and it will stay at 0. And until again it starts counting, it will be stayed at 0 because it got reset, and Q is 0, so it will be reset until we get another set pulse. It will not start counting, so it remains at 0. And this is what this is Q out temp. Now what happens is, after this got reset, this will trigger the minimum. So this is constant on time. So this is constant on time. Now when it triggers minimum off time will be set. So minimum off time will start counting, and whenever it reaches any minimum, it will be reset. Previously it was 0, and so whenever it is counting, Q will be 1, and whenever it has crossed n minimum, it will give a reset pulse, which will reset Q to 0. So if I use another color, say black color, now we have this T of minimum pulse. So this is the working. So the first part is generating constant on time, and the second part is generating minimum off time. So is this part clear how this is being generated?
Clear.
Okay. So this is that n minimum that SAR has put. So first part is T on, and the second part is T of minimum. And as there is a negation to this, only this Q out temp will be going into this Q out. So accordingly, this output will be depending upon Q out temp and Q out temp 1, Q out will come. So from this, I can see Q out will be, say if I use a different color, so my Q out will be here. So this is my Q out pulse. So this is the COT modulator, how COT modulator is working. Now, if we go into the Verilog implementation, so we'll just quickly go through. So the logic is important, how it is working. Implementation depends upon like our knowledge on Verilog. So if you know how to implement it, then we'll be able to implement. So all these things until this point, they are just a declaration of input, output variables and registers as well as wires that are needed. And from here, so this is being this block. Maybe I'll use a different color. So this enable and set reset is this block, Same as current mode control. So either positive edge on enable or positive edge on reset will enter the block. So if it is reset, output is 0. If it is set, then output is 1. So it is simple. Now we'll go into this counter. So counter we have discussed in clock generator as well as voltage mode control, current mode control. So we have discussed many times. So it is just the same code, but with the different variables. So this is this counter block. So this I can say it is constant on time counter. So it will count for constant on time and then it will be reset. So that code is being written for that. But the logic is this, that it is being counted and whenever there is a reset, it will be reset. Otherwise, it will keep on counting until the reset pulse comes. So this is the constant on time block. Now we'll go into the minimum off time block. So again, the SR flip-flop we have studied and the same thing. Always at the rate posit. So code is just copy paste. Only here it is Q out temp. Previously it is Q out temp 0. I mean Q out temp. Now it is Q out temp 1. So variable is changed, but the code remains same, exactly same. And again, there is less than a minute. So if this meeting ends, kindly quickly join so that we can continue our discussion. Now this counterpart. So again, the counter is exactly same as we had discussed or we have shown in the previous slide. Only the variables and other things change. See, if we want to show, we have this again reset. If reset is there, it will be reset. Otherwise, it will be keep on counting. And this is for off time counter, minimum off time, I would say. You are able to follow, right? Hello. Meeting, if meeting ends, kindly join quickly so we can continue our discussion. Are you able to follow? So it is just the same counter code. So counter code is always the same. So whatever we have written in the voltage mode control, current mode control, it is just the copy paste code. Only the variable names will change. Now there is something called clock manager. So if we go back, so the first module we were discussing about is the clock modulator, and the second module that we were discussing about is the clock manager. So clock manager is responsible for generating this enable. So here we have discussed generating the enable, right? So clock manager is giving me this enable signal for the clock modulator. So clock manager will be giving this enable function. So let us go into the clock manager. So the clock manager circuit is as shown. So first let us discuss about the clock manager, and then we'll come back to the Verilog code. So clock manager is enable. So enable is whenever QTR there is a positive edge, it should enable the clock modulator, right? So this is that part. So whenever QTR sees a positive edge, it will enable enable. So it will give a rising edge for enable. So another condition is say my current is on and then it is off, or maybe I should say so how the voltage mode control constant on time happens is during the on time voltage will increase, and during the off time it will hit the V reference, and so whenever it hits, that is being reflected over here, right? So what if there is some scenario, say this is my V reference, and after turning it on also, say this is my V naught. So after now here my constant on time ends. So now what happened? There should be this minimum off time, and then it has to turn on again so that it will cross, right? So this is the scenario that we had discussed in week 2. Why minimum off time is required? So this is the minimum off time, right? So now what happens is after this minimum off time, say after this minimum off time, at this instant, clock modulator should be triggered, right? So what SAR is doing is SAR is generating this reset pulse, or this reset pulse is the end of on time, and this reset pulse is the end of minimum off time, and SAR is naming this as F minimum. So at the end of off time, it will F minimum will have a positive edge trigger. So now SAR is checking whether QTR is 1 or not. Say in this case, QTR is 1, right? Because V reference is positive. So QTR is 1. So after minimum off time, SAR gets a trigger. So now SAR is adding this F minimum and QTR, and then using this positive edge to force trigger the enable. So this is the second part. So this is during the minimum off time. So after minimum off time, if it has to be triggered forcefully to turn it on, then we use this logic so that enable will be triggered and it will trigger our constant on time modulator. And the other part is external. So SAR has also put some external frequency, which is a fixed frequency. So if needed, if this F external is a fixed frequency. So SAR also has put fixed frequency pulses. So if none of this, like none of this is able to trigger it, then we are forcefully triggering the constant on time externally. So this is just a provision SAR has put, but it can be skipped also.
Please repeat it one.
Sorry.
Could you please repeat this point, like F minimum and F maximum?
So we have discussed in the voltage based constant on time that there could be a scenario where we have to operate off time for minimum off time, and then we have to turn it on, right? This was discussed in week 2. So now after this minimum off time, on time should be triggered. So after this minimum, enable should be triggered. So how this enable is triggered? So I am so the code is being generated in such a way, after this minimum off time, this queue finish is coming. So whenever off time is over, then this queue finish is coming. So this queue finish, SAR is calling as Fmin. So Fmin is the pulse or edge that is coming at the end of minimum off time. So at the end of minimum off time, SAR is checking whether QTR is 1 or not. If QTR is 1, then SAR is forcefully triggering the enable, because my V0 is still less than V reference and I have to turn on the COT modulator. So this part is responsible for force triggering the enable after minimum off time. And SAR also put some switching frequency external pulse, so that at fixed intervals of time period, it will check whether it has to force trigger the enable or not. So that's why this clock manager is very important, because it is generating the enable.
Like, sir, F minimum is here. Why this F external?
F external is switching frequency. So SAR is using another switching frequency, which will check at fixed interval of times that whether it has to force trigger the enable or not. Understood?
Oh, I am not clear with this F external.
So F external is like a switching pulse with fixed interval of time. So SAR is checking at this interval. SAR will check whether QTR is 1 or not, which means whether V0 is less than V reference. If V0 is less than V reference, then it will enable. So this SAR is put for additional extra safety, where there will be a fixed switching clock, which will keep on checking whether it has to force trigger the enable or not.
Sir, that is already like if
It is actually not.
Yeah. It is actually included in the Fmin and the QTR, right?
Yes, exactly. This is again not necessary, but SAR has put this for a provision. This 2 should be sufficient.
Okay, sir. Okay.
So this is our circuit. So coming into the implementation. So input, output, wire, all these are declaration. So then SAR has defined Qmin, which is QTR into Fmin, and Q external is QTR into F external. Then for this pause edge detection, SAR is using another submodule. Maybe I'll change the color. Something called edge detect. So there are 3 such edge detects whose outputs are again OR. So there is some edge detection function. The outputs of is OR. So first it is being declared, then these 2 AND functions. And then the next part is the positive edge detection. Positive edge detection. We'll come into this part, positive edge detection. And the last part is OR function. So this completes the clock manager. Now we'll go into the positive edge detection, how positive edge is happening, all these things. So edge detection is happening in this way. There is this Q in and the output is Q edge. So with respect to F clock. So let us draw the circuit. So again, these 4 are declaration. So every edge of F clock, SAR is doing Qt equal to Q1 and Q1 is equals to Q input. So SAR is creating some delay. So let us assume that Q in is like this. So this is, we already know that these are non-blocking statements, right? Or blocking statements. These are blocking statements. So it will happen sequentially. So say this is Q in. Then SAR is doing Q2 and Q in. So Q2 will be delayed by some time depending upon, so it will be delayed by one switching clock. So this is our Q2. So now what SAR is doing after getting Q2, SAR is doing XOR operation of Q2 and Q in. So if we do XOR operation, in this point it is 1, it is 0, in this point it is 1, and it is 0. So SAR is calling it Q3. So after getting Q3, what SAR is doing is SAR is doing Q3 and Q in. So Q3 and Q in. So if you draw this, so in this part it is 1 and rest of the part it is 0. So this is our Q edge. So if you see from this point to this point, we are getting edge, single edge, right? So this is like an edge detection. So this is the edge detection that we are writing in the Verilog code, which will give us the edge at that input. So if I have to write this in a block diagram or in the representation of NOT, yes.
Continue, sir.
Yeah.
Later.
Okay. So this is our Q in. So Q in XOR Q2, right? So this is like a delay. So we have inserted one clock cycle delay. So Q in XOR delayed version of Q in, and the output of that and Q in doing AND operation, it gives us QH. So this is the complete representation of this code, and this is the timing diagram. So timing diagram is very crucial, because of which we can understand what exactly is happening and how the edge is coming. Yeah, someone was asking a question.
Sir,
Yeah.
in this Q2 should advance Q in, right, sir?
No, like say initially Q2 is equals
Anyway,
to Q1.
QEJ will remain same.
Yes.
QH will remain same. But this Q2, based on this sequence, Q2 should advance Q in, right?
No. Say like initially all the registers are 0. So in the first clock cycle, Q2 will be 0 and Q1 will be Q in. And in the next, like whenever again this loop starts, then Q2 will be Q1, which is Q in. Understood?
Okay.
Either way, you can write Q2 equal to Q1. It is just the same thing.
Yes, sir. But when Q2 equal to 0 initially, when
so like say in the say loop number 1. So loop number 1, we are entering Q2 is equals to Q1. Initially all Q1, Q2 are 0. So Q2 is equals to 0. And then Q1 becomes Q in, which becomes in the next cycle Q2. So Q1 has become Q in. So at this instant, Q1 has become Q in. Now in the next cycle, Q2 is becoming Q1, which is Q in. So that this delay is happening.
Sir, actually, first this that Q2 equal to Q1.
Yes.
This will happen at the first positive edge.
Yes.
And again, this Qn equal to Qn will happen at the second positive
edge. And then at the third edge, Q2 will become Q in. So that will decide this delay.
So actually 3 clock pulses.
Yes. 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 At the third clock, like say this is Q1 or this is a Q in. So at this say 1 clock, second clock, third clock. So at the third clock, I'll use a different color. So at the third clock, Q2 will update, right? First clock, Q2 becomes 0. Second clock, Q1 becomes Q in. Third clock, Q2 becomes Q in, right? So it has like 220 nanoseconds. But again, it is up to you. If you want more delay, we can put more delay. Is it part clear?
Yes.
Again,
At the point.
yeah.
That's allowed, okay.
Yeah. Please.
Sure. Like at the first positive edge of the X clock, Q1 is becoming Q2.
No, Q2
Then
is becoming
this
Q1.
Qin equal.
Q2 is
Q1
becoming
is
Q1.
becoming Q2.
No. Q2 is becoming Q1.
So okay. Q1 is being assigned to Q2. Like when this will this Qin will not be assigned to Q1 in the first positive edge of the clock itself?
No. So if I draw Q1 also, so this is Q1.
They're blocking for one positive edge.
Sorry.
Sir, what I am thinking is if the frequency of the clock is 20 seconds, let's say.
No. Frequency of the clock is 10 nanosecond.
Okay. Like, sir, Q1 is being assigned to Q2.
Yes.
How much time it will take, sir? Like, for how much time it will block?
Oh, actually, I think you are right. So for the first clock itself, this will happen and then this will happen. Sorry, I think it will not be the second clock. Yeah, you are right. So this is inside the F clock itself. So yeah, thanks for correcting. So what happens is at the first clock itself, first Q2 will be updated. So Q2 will be 0. And say this is Q2, this is Q1. So Q1 will be assigned with Qin. So this is Qin. So Q1 will be same as Qin. And in the next clock cycle, Q2 will be updated. Because they are in the same positive F clock. Understood? Like once this clock is detected, both are being
this is
executed.
non-blocking, right?
This is blocking, but see at the positive edge of clock. So at this clock edge, first this will be executed, then this will be executed, right? But at this clock edge only, both the execution will happen. But first Q2 will be assigned, then Q1 will be assigned. But both of them will be executed at this F clock. Understood? So both are coming under the same positive F clock. So whenever there is a positive on the F clock, first Q2 will be assigned with the Q1, which is 0. And at the same instant, Q1 will be assigned with the Qin. And in the next clock cycle, Q2 will be assigned with the Q1 and Q1 will be assigned with the Qin. So the delay is 10 nanoseconds. Banerjee, thanks for pointing this out. Yeah.
Sir, here what will happen if there is a blocking statement here? Sorry, non-blocking.
Then both Q2 and Q1 will be assigned at the same time.
So there will be no delay in Q2.
That we have to see. So Q2 will be assigned with the Q1 and Q1 will be assigned with the Qin. So at that instant, what is the value of Q1? That will be assigned to Q2, and what is the value of Q1? That will be assigned to Qin. So, so at this instant, Q1 is still 0. So Q2 will be assigned with 0 and Q1 will be assigned with the Qin. Yeah. So one thing I would recommend you is do not assume that like this is happening. I ask you to write the code and see and do some manipulation and see whether your logic is happening or not. Understood? Like if you just think that, okay, this is happening, then this is happening, you will not learn anything. You should start writing the code and see whether your logic is actually working there or not. Okay, so your queries are clear, right? Until this point?
Yes.
Okay.
Okay, sir.
Yeah. Now we'll go. Yeah. Okay. So now we'll go into the hardware results of whatever concept that we have studied till now, and input is 3.3, output is 1, and frequency is variable, and this is being operated at light load condition. And these are the controller details. Actually, we are not using any control. So one is ADC, F clock, and KF. So And this is operating in constant on-time voltage based, and it is operating in light load condition. Also, it is in DCM operation. So this is one such scenario, and at some point of time, sir has observed this behavior, which is this is T on, and this is T off minimum, and this is T on. So after T on, minimum off time has happened, and the V output is still less than V reference. So during on time, it has increased, and after minimum off time, it is still like after this first on time, the V naught is still lesser than V reference. So forcefully after minimum off time, we are turning it on again. Now it has crossed, so again it has turned off. So this is one case where minimum off time has been observed. Minimum off time has been observed. So in the rest of the part, it is happening like this: on time, then off time it is hitting, on time, off time it is hitting. So this is V naught, and this is V reference. But in this case, the V naught is lesser than, say this is V reference. V naught is lesser than V reference after the on time also. So that's why it needed another on time consequently after minimum off time. So there are two such on time happening next to each other with minimum off time separation between them. So this has been observed in the hardware as well. So this point is clear, right? Hello. Hello.
Yes, sir.
Okay. So now till this point, we have seen the digital voltage mode control. So fixed frequency. We have seen voltage mode control and current mode control. And in variable frequency, first we have seen the voltage based constant on time. Now we will see current based or current mode control. So in current mode control, we look into two things. One is the constant on time. One is the constant on time. The other one is the constant off time. Okay, so in the first part, like we'll not go into the Verilog part as I has not discussed. We'll see, we'll thoroughly discuss about its architecture, and then we'll see the FPGA implementation and a few experimental case studies. So all these constant on time, off time, why minimum off time is needed, why minimum on time is needed, all these aspects we have discussed in week 2 of this lecture. So this is the YouTube link of our discussion. You may refer to that if you have some difficulty in understanding. But to summarize, we have unlocked a digital converter, and then the output is subtracted from the V reference, giving to V error. Then we use a PI controller, and then we have discussed about event based. Why event based? Because it is variable frequency. All the aspects we have discussed in week 2 as well as week 3. And then it will give value, because constant on time means it is a value current mode control. And so we have also discussed this nomenclature and everything in week 2. So this is very crucial. If you still face some difficulty, I suggest you to go through this week. And after this value is compared with the IL, which will give event. This is the event triggered. So whenever this inductor current hits this I reference, that is act like a event. So this is one event, and this is the other event, and this is the other event, and this is the inductor current. So now this goes to the COT modulator, constant on time modulator, with minimum off time, as well as output has dead time. So this part we have discussed, but I have just summarized quickly. And if we see the FPGA implementation, so it will be similar to what we have discussed in voltage mode control, except there will be another loop, which is the current loop. So first part is V naught with gain coming to V feedback, analog to digital converter, and then ADC DAC 10-bit. then we will store in some register, and then we subtract from the V reference to get the error voltage generation. So error voltage, which will then go to our PI controller. This will give current reference, and then we have discussed in current mode control. We had some current reference block to put saturation. Also change the format from 2's complement to offset binary. So this is that block. Now this reference is generated like is passed through DAC, which will give analog. Now these parts are in analog domain. So all these parts are in analog domain. So it is being compared, and then after being compared, it is going to the modulator because the output is the event. So that event, so this event will trigger this, say this entire thing is the COT modulator. So this is the COT modulator. So that event will trigger the COT modulator, and then COT modulator will finally generate this PWM high, PWM low with red time. So this is the zoomed in part of that. So this is that additional thing that is coming with respect to our voltage base. In the voltage base, we don't have this additional circuitry because it is only single loop, but here we have this current loop. So DAC compared with the inductor current, and then going with the COT modulator, and then dead time, and then which finally generating the gate pulses. So all these are coming from this architecture, which you can refer if you want in week 2. So till this point, it is clear, right? Hello. Hello.
Yeah, yes, sir.
Okay. So now we'll again go into hardware results. So here sir started with 2.5 volts, output 1 volt, and variable. As you know, COT current mode control is a valley current mode. So this is the valley current mode. We have to set, so SAR is running in constant I reference mode. So SAR is giving constant I reference and then running it. So constant I reference SAR has set 2 amperes. And this is the on time that SAR has chosen because it is constant on time, and this is the minimum on time that SAR has selected. And if we see the hardware results, SAR has considered a case study where SAR is reducing the V input. And what are the observations that SAR has found? If you see, this represents the switching frequency, right? So this is the switching frequency pulse. And SAR has noticed, it is noticed that with reduced V in, so as V in is reduced, switching frequency is increased. So how, why it is increasing, how it is increasing. So we'll come to this. So this is at steady state, right? So at steady state, a ripple is same. So V in minus V naught into T on by L is equals to V naught into T of by L. So now if you bring T on this side and make some mathematical manipulation, we will get this expression. So FSW is 1 by T on into V naught by V in. Assume that V naught is almost constant. It is not constant, but assume it is almost constant. And this is constant on time, right? So T on is also constant. So it is like FSW is some constant by V in. So FSW is inversely proportional to V in. So if we reduce V in, then what will happen? Switching frequency will increase. That is again, that is what is observed here. So there is some increase in the switching frequency, which is because of whatever control technique that we have selected. It is related with V in inversely. So when V in is reduced, switching frequency is increased. That also is observed in the FFT. Now, if you see the ripple here, the ripple here, and the ripple here, and the ripple here. So inductor current ripple is decreased when V in is increased. So how do I capture it? I know that delta IL is equals to V in minus V naught into T on by N, right? So if I have to say delta IL, V naught is almost constant, L is constant, T on is also almost constant. No, T on is constant, V out is almost constant. So delta IL is proportional to V in. So if V in reduces, delta IL reduces. So that is what is happening. This Vin is reducing and I delta IL is also reducing. So what is the observation? The observation is that if input voltage decreases, switching frequency increases. And if input voltage decreases, inductor current ripple also decreases. So that is being captured from this mathematical analysis also. Okay. So until this point, is this clear? Hello.
Yes, sir. Please.
Okay. So this is the constant on time which signal current mode control. Its counterpart is the constant off time current mode control. So again, it has constant off time, which means minimum on time. Also, it is a peak current mode control. It is
Sir,
just
here, like, why the event is also being censored, sir? It is already included in the positive edge, right? But why it is event?
see this event is whenever this touches this, right? So if I go back, I'll just compare. It is not the exact thing, but I'll just compare. See, this is QTR, right? So whenever we notice touching V reference, that is this QTR. The positive edge of this QTR triggers this COT, right? So that is what
That
we
is
have.
fine.
Yes. So that is what we have seen also here. The positive edge of QTR will enable it. Similarly, if I come back to constant on time, say this is peak current mode control, and it is constant off time.
Okay.
So whenever this inductor current is touching I reference, I have to get the information of this event so that this event will trigger my constant off time modulator. So after whenever this touches, my code should know that yes, IL has touched I reference. Now it has to turn off for fixed amount of time. So how will it know? It will trigger this event. So this is the compared output of the comparator, this event. Again, in the similar way, how it has been done in the voltage mode control, that pause edge is observed and it went to the enable. This enable will trigger this constant on time in the case of constant on time. It will trigger the constant off time in the case of constant off time. So that's why we need that information. Is that clear, Banerjee?
Not clear, sir. Actually, when the comparison is done, there will be a rising edge and there will be a positive edge, that is clear.
Yes.
But for minimum on time, why there are two inputs? That is my question.
Minimum on time.
Yes, sir. For minimum on time block, there are two inputs, right? One is positive edge and the event. Why you are mentioning two?
Okay, actually, this has come from the MATLAB model. So in the MATLAB model, did you remember our MATLAB model?
Yes, sir. I remember.
So in our MATLAB model, so this is coming exactly from our MATLAB model. So it has two blocks next to each other. One is the minimum on time, the other one is the monoshot timer. So these are the inputs. So the MATLAB model that has been made in such a way that it
for minimum on time, the ending of the monoshot timer is taken as input.
Yes, exactly.
Okay, sir. Okay, that's clear. Thank you.
So this has come from the MATLAB model, but it is again the representation, but you can completely put a single block saying constant off time with minimum on time. It is again the representation which can change from person to person. So, but as we are referring to our MATLAB models and we are following the same picture throughout the course, we have used the same picture. Again, why minimum on time is needed? All the MATLAB models, you can either go to week 2 or you can go to week 3 or week 4, where we have discussed the MATLAB simulation of the same. Now again, this is peak current mode control. So everything will be same. So that's why we will not go into this, except this COT modulator is constant off time modulator or constant on time. In the case of constant on time, it will give constant on time and then it will off, right? So this is constant on time. Here also, it will do the same, but we need constant off time. So that's why, so what it does is, it will give constant off time. For constant off time, it will be 1, and then for on time, it will be 0. But we want the exact opposite thing. So that's why there is a comparator put. So what it does is, it will invert. So for constant off time, it will be off, and then it is on. So that's why this inverter is responsible. So the code is written in such a way that output of the COT modulator will be like this. But we want the exact opposite thing. So that's why inverter is put. And this is just the same thing which we have discussed for constant on time, except there it is valley current mode. Here it is peak current mode. And if you want, you can refer to this. So again, with 2.5 input voltage, it is started. Output is around 1 volt, variable switching frequency. Now it is a peak current mode, right? So accordingly, the reference has been chosen. Previously, it is a valley current mode. Now it is peak current mode. So a 3.4 amperes peak has been chosen. So inductor current ripple is around 1.4 amperes, it seems. So the valley is 2 amperes. Say the ripple is 1.4 amperes, say approximately at that particular instant. So value will be 2 amperes and peak is 3.4 amperes. So the same has been considered for the hardware result. So for 2 amperes, this is let me change the color. So we have a question. Okay, yes. So this reference value is for constant on time, and the peak is for constant off time. Okay, so the same has been considered, and the T off is 2.6, and T on minimum is considered 0.1. Using the same, the hardware results are considered, and if we consider the same scenario where Vin is reduced, so here we some other different observation has been observed that as Vin is reduced, switching frequency also reduced. If you see here, it is happening at this point, the main harmonic, and it is going left. This is the switching frequency. This is also switching frequency. And this is also switching frequency. So it is going left, which means it is decreasing. So if Vin reduces, Vin is reducing means switching frequency is also reducing. So that is observed. So now we have to justify it why it is happening. Coming to the another thing, if you see delta IL, it is just the same thing in all the three cases. It is not dependent on Vin. Delta IL is same in all the cases. So why is it happening? Is it correctly happening, or how to justify, how to explain this behavior? Again, Vin minus V naught into T on is equals to V naught T of Y. If you just manipulate it and change it so that it will have switching frequency as well as T of turn, you will get this expression. So now this expression tells me something. Say V naught is almost fixed. So say V naught is almost constant. And T of is constant. Now, if Vin reduces, this fractional value increases. So 1 minus this value will again decrease. So when Vin decreases, switching frequency is also decreasing. So that explains this behavior. So my first observation that Vin decreases, switching frequency also decreases is explained from this mathematical expression. Now coming to the ripple part. So ripple part, I would consider delta IL. There is less than a minute. If this meeting ends, kindly join so we can discuss the final part of this presentation. So delta IL is V naught into T of by L, right? So this is my delta IL expression, which says T of is constant, V naught is almost constant, L is constant. So delta IL is constant. Delta IL is independent of VL. So that is the observation. If input voltage decreases, frequency decreases, and inductor current ripple is independent of input voltage. So till this point, is this clear? If this meeting ends, kindly join. Till this point, is this clear? I think.
Yes, sir, we can proceed.
Okay. So I think this meeting will end. Hello.
Sir, audible and visible.
Okay. Yeah. Thanks for confirming. So this completed this part mixed signal current mode control, constant on time based as well as constant off time based. Now, these are the observations. So the observation says that in fixed frequency, switching frequency is constant.
Sir, in
Yeah.
the previous slide, like how you derived FSW, sir, could you please repeat it once?
So this is just like T on, you can write it as T minus T off, right?
Okay.
Yes. Now you substitute this in the equation, then you'll get this expression. So just give it a try.
Okay, sir. Thank
This
you.
should give
Thank
that
you.
expression. Now, the observations are in fixed frequency is constant, because that is what fixed frequency means. So it is insensitive to V input and output. In constant on time, we have seen that highest switching frequency happen at lowest input voltage, and for constant off time, we have observed that switching frequency and input are proportional. So highest switching frequency will happen at the highest input voltage. So these are the observations and also the mathematical validation.
Like if the input voltage is fixed and if the output voltage is varying,
then it depends. See how
like
much varying. See, switching frequency depends on V naught by V in fraction. Usually, our circuit is in such a way that output is always regulated, even if V in is slightly more than needed or slightly less than needed. So output is almost constant, right? So under that scenario, assuming that V naught is constant, T on is already constant. So the only variable is V in, which can be, say, for 12 volt input, can vary from around 8 volts to 15 volts. So if V input varies from 8 volt to 15 volt, switching frequency will also vary. And we are checking how switching frequency will vary. Input, if it reduces, switching frequency increases. So what is the highest switching frequency? It happens at the lowest input voltage.
okay. Sir, if you are teaching these many techniques, like for particular applications, which have to pick up.
Yes, again, there are so many control techniques, nonlinear techniques, linear control techniques, but which one suitables that application, that again the designer has to take the decision. So these all are the basic control techniques that we are teaching in this course, which are almost like these are the control techniques that cover majority of the products. Also, majority of the products they use voltage mode control, fixed frequency, or current mode control, or constant on time. This is again very popular control technique that is used in many products, and constant off time also. So depending upon their application, there could be some reason why they are going for constant on time, constant off time. So depending upon that, they choose that constant on time, constant off time control. Again, it is not like that you should only use fixed frequency or variable frequency. So everything has pros and cons. So depending upon your application, considering both pros and cons, one has to select one control technique and implement that control.
The constant on time or off time comes into picture when there is a load transient only, or even the source transient also will be come into picture.
Sorry.
Like in the MATLAB simulation, what I came to conclude from this constant on time and off time comes in when there is a step transient in the load current. That is the thing what I have observed.
Okay.
But will these constant on time and off time come into picture even if there is a change in the input too?
If there is a change in the input,
will these come into picture? Constant on time and constant off.
Like, I am not following the question. Can you please repeat?
It's a constant on time and off time will be observed when there is a change in the load current.
Yeah.
Otherwise, if there is it is under steady state, we can't observe any change in the off time.
Yes, you are right. Absolutely
in constant on time, and in constant off time, the change in the on time is observed only in change in transient case.
Yes, you are absolutely right. So in the steady state, switching frequency is constant. So FSW is constant. Also, whatever on time, off time you have considered, they will also be constant because it is steady state and switching frequency is not same. So if I give you a switch steady state picture like this, say if I give you only this picture, we cannot say whether it is constant on time or off time. So when there is a transit from there, we can only see whether on time is constant or off time is constant, or the frequency itself is constant. So depending upon that,
Okay.
we'll come.
I observed this only when there is a
Low transit
node tangent.
or reference transit.
Can I observe the same if there is a change in the input voltage too?
Yes, say if there is input voltage, say like I inductor current, if there is any slight disturbance, then it will come back to its steady state. So from during this, whenever the disturbance happened, then I can get the information whether it is constant on or constant off or fixed frequency. But if that V input happens very slowly, then switching frequency is almost constant and will not. So till now we have considered different kind of control techniques. First to start with fixed frequency, then variable frequency, both voltage mode and current mode. But before going into the adaptive on time, let us have a brief overview of light load control architectures. So one is PFM, pulse frequency modulation, pulse skipping modulation, burst mode, and hysteresis control. So these are the light load control techniques: PFM, PSM, burst mode, and hysteresis. So in PFM, one popular control architecture that is used in many of the products is adaptive on time, which we'll discuss in the upcoming slides. The other one is the PSM. So it has either a skip pulse or charge pulse. So it has either skip pulse or it has charge pulse, and this we have discussed in the last week, where we have implemented the digital PSM also. And in digital PSM, we have one V0, one V reference, and one comparator. So either if V V0 is more than V reference, it will skip. If V0 is less than V reference, it will charge. But in the case of burst mode, it has a hysteresis. So V0 has a hysteresis. So V0 will be here, and V0 has upper limit VH and lower limit VL. So whenever it hits upper limit, then either it will give set reset, or whenever it hits the bottom, then it will generate set pulse. So accordingly, the gate pulse will change. So here we have only one comparator. Here we have two comparators, so upper limit and lower limit. Similarly, hysteresis will have, if you say current hysteresis control, so there will be two, this also we have discussed: current hysteresis, mixed signal current hysteresis, peak, valley, average. So they will have this I peak and they will have this I valley. So the current will be, if I change the color, so and say if it starts from here until it hit, it will on, then it will be off, on, off, on, off. So this is another light load control architecture, not so popular, but this is the most popular architecture, which is the adaptive on time pulse frequency modulation, because frequency is variable. So they call it pulse frequency modulation. And one such thing is adaptive on time. So this is the background story of adaptive on time, and we'll discuss more on this PFM. So this is some
What is the difference between burst mode and the hysteresis?
So here they have this voltage hysteresis. Here we have current hysteresis.
Okay. Okay. Sir, this PFM, like, could you please explain one?
Okay, so PFM is pulse frequency modulation. So then name by pulse frequency, because frequency is being modulated. And one such architecture of PFM is the adaptive on time, where on time they will adapt, and how they are doing, what is adaptive on time, we will discuss. And adaptive on time is one such example. So this is light load control architecture. So this is operating in DCM, as you can see. And the further details we'll discuss in the upcoming slides. So now we'll discuss about the adapt to on time. As we have discussed, it is light load control technique. And first we'll discuss design methodology. Verilog HDL I will not touch because we are running out of time, and then we'll discuss the hardware results. So what adapt to on time mean is, say we have considered constant on time. So constant on time, what it is doing, constant on time, if I go back here. So in my constant on time, the output, the inductor current ripple is dependent on the input voltage, right? So say if we don't want this, we don't want the inductor current ripple to change with the input voltage. Say if inductor current ripple wants to be fixed. So then what they do is, in adaptive control technique, they fix the peak. So as you can see here, they fix the peak. So whenever the inductor current starts from 0 because it is DCM. So it will keep on increasing until it hits peak. Then it will be turned off 0, and then again it will start. So here I peak is constant. T on they are adapting. So T on will be adaptive because M1 is what? M1 is, let me change the color. So M1 is V in minus V naught by L. Say if V in increases, slope will increase. So now this becomes the T on and it will fall. If V in decreases, then slope will become slow and then T on increases and fall. But delta IL remains same. So the main objective is to keep the delta IL same. So that's why they're fixing the peak and they're changing the on time adaptively. So this delta V naught expression, this is coming from the buck converter. If you derive from the buck converter, you will get this delta V naught. And now it is dependent on T on. So now we are fixing, now we are adapting T on based on I peak. So if you write T on, it is I peak by M1. M1 is what? V in minus V naught by L. So if you substitute that here, we will get this T on. Now if you substitute T on in this equation, then you will get this expression where delta V naught is Li peak square by 2 CV naught. So this is the voltage, output voltage ripple when it is operated under adaptive on time. So this is the basic introduction about adaptive on time. Now if you go into the Verilog implementation, so this is the buck converter, and so this is the adaptive on time control. So what adaptive on time is doing is, this is what? Inductor current, right? So whenever the inductor current touches I peak, it will generate one event, and based on that, off time should start. So that is what is happening. So they're comparing that I peak. So this is the I peak. They're comparing the I peak with this inductor current. So whenever IL touches the I peak, so whenever IL touches the I peak, it will trigger and the off time will be started and it will be 0. And then that comparator is going into this adaptive on modulator, and accordingly it is generating this dead time and the other circuitry that is needed. So if you go into the Verilog module, so Verilog module will be completely similar to the constant on time current mode control. So it will be completely similar to constant on time current mode control, except the part here on time is V independent, whereas in the case of constant on time current mode control, it is not V independent. So again, the adaptive on modulator. So this constant on time PFM has sub block similar to constant on time current mode control, which has again the COT modulator. So this is the COT modulator. So this is the adaptive on modulator. Again, I'll not go into the details of Verilog HDL because it is a special case of constant on time current mode control, and the Verilog part of this.
Sir,
Yes, sorry.
Sir, here we are adapting the on time to keep the output voltage band within the limits, right?
No, we are adapting the on time such that delta IL is same, I peak is same. So I peak we are fixing, and based on that we are getting the on time.
But okay.
And delta V naught is this expression. So depending upon the I peak you have chosen, delta V naught will increase.
Okay.
So you have to select the I peak in such a way that delta V naught will be in the within range, or you have to select the capacitor accordingly.
Okay.
So and it has adaptive on-time modulator. Now we'll discuss about the adaptive on modulator. So what contains in the adaptive on modulator?
I have a doubt. Like
Yes.
in constant, how we're gonna fix the on time? This is the constant on time I need.
Yes. So this is also constant on time. So adaptive on time means on time is constant as long as V in is constant. But if
Okay.
V in changes, constant on time will change to new constant. Again, it will be constant.
Okay, that is clear. Like in the constant on time control, what we have discussed in the previous lecture, the monosort timer we are loading it to the constant time to which we want constant on time, right? There, what is the factor that is going to decide this is the constant on time we need?
Constant on time.
We need, like
Yes.
what we meant. How we gonna decide that T on?
Like T on value.
Yes, sir, exactly.
Okay. So how are we deciding? Say we know, say I'm considering say 12 volt to 1 volt buck converter, and I need I peak to be say 1 ampere. Usually input varies from say 8 volt to 15 volt, I can say, and I want I peak to be 1 ampere. So my on T on into M1 is equals to I peak, right? So T on is equals to I peak by M1, which is V in minus V naught by L. Yeah, so this I peak into L by V in minus V naught. So this will give us our T naught. So as input is varying, so for 8 volt it will have 1 T on, and for 15 volt it will have different T on. So that T on is being calculated by our controller itself. So the controller will take care such that peak is remains same and on time is variable.
Sir, here we are actually saying this del V naught is less dependent on this T on, right?
Del V naught is dependent on T on, but T on is again
less
dependent on
dependent.
I peak. Did you understand?
Yes, sir. But sir, here we are making the inductor band to be equal.
I peak
to be
delta
equal.
IL is same.
So we are making delta L to be same.
Hmm.
For keeping this, we are changing this T on.
Yes.
Then what is the difference between constant on time and this one?
See, in constant on time is always fixed, irrespective of the input voltage, and
Yes, sir.
ripple will
That
change
is clear.
dependent on input voltage. But
Yes,
here ripple is always constant and on time is adapted. On time is constant, but it varies with the input voltage. For a fixed input voltage, on time is fixed. If the input changes, then on time is again fixed, but it is a new value, not the same value.
Okay, that is clear. But in constant on time model, like what you are saying, sir, adaptive on time control itself. So we have discussed the constant on time. It is included in this adaptive on time.
Sorry.
Like I'm confusing between the constant on time and the adaptive on time controls.
Like what is your
Adaptive
confusion?
on time control, it is clear. Based on the input, the on is changing.
Yes.
But I'm considering only constant on time control.
Yes.
But my input has some variation.
Yes.
In that case, what's gonna be the on that is constant over the entire band of the input?
See, in the constant on time, on is fixed irrespective of the input voltage, and it is fixed throughout. But in the case of adaptive on time, on will adapt based on the input voltage, but it is also a constant. Say input is 12 volt, then on will be fixed to this value. And if say input is 8 volt, then it will be fixed to that value which you will get from here. on is always constant, but here we are changing on with VL so that our I peak is constant. So for fixed
Yes, sir,
VL,
that is
our on time
clear.
is fixed. Yeah.
Yes, sir. In adaptive on time, it is clear. Moving to constant on time.
Okay.
What is the on constant value? We
Okay.
are considering.
Okay. So you are asking how to choose the constant on in constant on time.
Yes, sir.
Okay. So coming to your question where we have constant on time. I'll take a formula from the previous slide. So just okay. So delta IL is V in minus V naught T on by L. So I'll write this. Delta IL is V in minus V naught into T on by L. So I know that for a fixed application, I will decide the maximum worst case scenario of delta IL, right? So I will say delta IL maximum should be say 2 amperes. And when will this delta IL maximum happen? Maximum input or minimum input?
Minimum input.
Minimum input or maximum input? V in
maximum
maximum.
input.
Yes. So we'll consider this scenario and then we'll calculate the T-on. So at the worst case ripple, what should be the T-on? So now if I say T-on is delta IL into L by V in minus V naught. So I'll consider the worst case scenario and I'll calculate the T-on. Okay. So
okay, sir. Clear.
Yeah. As if the on time is fixed, if the input voltage is maximum, ripple will be maximum. So for my given on time, even if input voltage is maximum, my delta IL will be at this 2 amperes. But if Vin is lesser, then ripple will change. So that is what we have observed here, right? Say this is ripple is say 1.4 amperes. So I have designed the converter in such a way that this is the maximum input voltage at which my ripple is 1.4 amperes. Accordingly, I have fixed the on time. Now, if Vin is reduced, ripple will reduce and ripple will still stay within the given requirement. So I will design the on time for the worst case scenario. Every time we'll design it for the worst case scenario. So the same thing has been done. I am designing T-on such that for the worst case, whatever is the delta IL, that will stay within the limit. Okay. Now that being clear, we came into this adaptive on modulator. So constant on time and minimum off time. So if we draw the constant on time, and then so in the case of constant on time is constant, right? But in the case of adaptive on time, the on time is coming when inductor current touches I peak, right? So whenever inductor current touches I peak, I should turn on the on time. So that is being happened. So enable will come, say enable came at this instant. So enable came at this instant. Now now Q will be on. So enable came at this instant. So if I draw the enable, so enable came at this instant. So Q will be on. So whenever this IL touches the I reference, reset pulse will be given. So at this instant, there will be a reset. So my Q will be reset at this instant. So again, there is no counter needed here because my on time is not coming from the loop. Instead, the on time is coming from the I peak and IL. So that comparator is acting as a reset and enable is acting as a set, and no counter is needed. Because it is like a peak current mode control. We can say it as a peak current. Let me change the color. So this is like a peak current mode control, right? So whenever it hits the peak, it is turning off. So this is like a peak current mode control. And this is the implementation of peak current mode control. So if you check the previous lecture, peak current mode control has one SR flip-flop, which we have implemented in the Verilog coding. And the minimum of time remains same because for minimum of time, we need a counter. So it has one SR flip-flop and then a minimum counter. And this also remains same as the previous constant on time. So only this block changes. So only difference is this block, which the on time is coming from the inductor and I peak comparator instead of a counter directly. So that is the only difference in constant on time and adaptive on time. And entire part same. So is this clear until this point? Hello. Hello. Hello.
Yes, sir. You can proceed,
Okay.
sir.
Okay. So now that adaptive on time we have discussed. So SAR has considered another case study where SAR is reducing the input, but peak will be same, right? So peak, I think SAR has considered 1.2 or 1.4. I'm not sure.
Last case,
1.2 amperes. So
sir.
yeah,
Sir, in the last case, when Vin is increased,
yes,
sir, this T on will be reduced to keep IP constant, right, sir?
yes,
That is what we are doing there.
yes. So if yeah, I'll draw this diagram again here. Say my I peak is constant. Now I'll consider three scenarios. One is like this. So this is the on time. And say if Vin is increased, then slope will increase. I think I should have used a different color. So let me use dark blue. So when Vin is increased, so it will hit faster because Vin is more. And if Vin is less, then it will hit slowly. So that you can see if Vin is high, it will hit faster. If Vin is less, then it will hit somewhat slower. That is what is being observed. But again, the peak is set to 1.2 amperes. This is being set by SAR. So this will set, and accordingly the closed loop will take care so that the peak is remained same. So here now peak is independent of V, and yeah, on time we are adapting. So that's why the adaptive on time thing. So until this point, is this clear?
Yeah.
Hello?
Yes.
Okay.
Yes,
So
yes.
I'll summarize what we have discussed. So we have considered wide range of control techniques for today's discussion. So I can categorize this into three. So one is the fixed frequency, and then we have discussed variable frequency in general, and then in the variable frequency, a special case, the adaptive on time. So that's why I'm separating it out. Now, if we come back to fixed frequency, we have seen two architectures. One is the digital voltage mode control, and the other one is the mixed signal current mode control. Here, variable frequency again, we have discussed two things. One is the voltage based constant on time, and the other one is the current based or current mode control. Current mode control. Now in the current mode control, we have again seen two different things. One is the constant on time. The other one is the constant off time. And adaptive time, we know we have considered different case studies. So delta IL is constant and T on is set accordingly. And we have seen Verilog HDL of few cases and experimental results of all the cases. And we have seen different scenarios, how the input voltage affects the ripple, how input voltage affects the switching frequency. So now let us solve a few problems. I have considered two problems. So first one is the adaptive on time, as this is again very crucial and very important topic. So I have considered a buck converter with input 11 volts, output 1 volt, L to be 229 Henry, and I peak is 2 amperes. So now how will I find the on time?
L into I peak by.
Yes. So T on is I peak by M1, right?
I peak by M.
Yes.
M1 V in minus V naught by L.
I peak by M1. So it is L into I peak by V in minus V naught. So L I have given 220 nano Henry. So 220 nano. I peak is 2. V in minus V naught is 10. So on time should be 44 nano Henry. Sorry, nanosecond. So this is the on time. And I have asked what is the capacitance required to maintain 1% as the output ripple. So we know the formula. So this is the formula that we have used for T on time. And similarly for delta V naught, we have this formula. So if you substitute 1% means 0.01 volt is equals to 220 nano into I peak square, which is 4 by 2 into capacitance into V naught is how much? 1. So 2 times. So C is equals to.
Sir, how this formula, sir?
Okay, I'll come into 10 square. So we'll have 220 into 10 to the power minus 7. So if you do into 10, so 10 to the power minus 6, so it is like 22 microfarad. So this is the capacitance requirement to maintain this much of voltage ripple. So that is the first part on time, second part capacitance requirement. So now coming back to your question. For a buck converter, so for a buck converter,
Sir, it is 44 microfarad. How much is the answer, sir, for capacitance?
Sorry, there is this 2 also. Your rate is 44 microfarad. So in adaptive on time, there are two things. First thing is the adaptive on time control technique and the converter where we are applying. So we are applying for the buck converter. So for the buck converter, you can derive this expression of delta V naught, which has been discussed in one of the lectures, I think first week, or you can refer to the previous course also, or it is online available. So you can get this expression. Now for adaptive on time, the on time is related by this expression. Now, if you substitute this in this expression and solve it, then you will get this expression, which I have not shown, but you can derive. Just you substitute this and you will get the simplified expression. Is that okay? Hello?
Yes, sir.
Okay.
This is okay, sir. This derivations are
okay. So derivation.
Actually, what I remember is, like I have an expression in my mind. There will be an 8 in the denominator.
There will be 8.
Yes, sir.
How
in
come
terms of FSW, like V equal to QC.
from the charge balance, if we derive from the charge balance, I think it will become some 8 FC, something like that will come.
Yes, sir. Delta V equal to Q into delta Q into C. Delta
okay,
Q by C.
I think one mistake you might be doing is you are doing for CCM. Again, you have to remember this is DCM.
Yeah.
So
Yes,
you
yes,
have to
sir.
consider.
Yes, yes.
You have considered this, or maybe you can cross check your calculations. So they'll not be exactly same thing. It could be, it will be somewhat different. So again, do it for DCM, then I think you will get.
Yeah.
Okay.
So do it for DCM. V ripple is equals to constant, then I peak equals to constant. No, V ripple is not constant, Shankar. I peak is constant, and V ripple is not constant. And considering I peak to be constant, we have derived this V ripple, and this is the condition. So now my question is, if capacitance ripple should be 1%, what is the value of C? And the value of C is turned out to be 44 microfarad. So hope this question is clear. Now we'll move on to the next question. So the next question I have given something like matching. So fixed frequency current mode control. So whether frequency increases or decreases with the input voltage, or it is independent of input voltage. So just to summarize, these are switching frequency lines, and these are delta IL lines. So each one of them will be related to one of these three or one of these three. So fixed frequency, out of these three, which one it is related to? 1 or 2 or 3?
3. First one is 3.
And inductor current ripple, let me take this here. So
Yes.
in the fixed frequency,
Third one.
third one, inductor current ripple is independent of input voltage, or what
No,
can
for
you say?
fixed frequency,
Yeah, like you can consider V in minus V naught into DTS by
yeah,
L.
L.
And say V naught is constant. Duty ratio is what? V naught by V in, right?
Mhm.
So if you write V in minus V naught into duty ratio, which is V naught by again V in into TS by L. If you multiply, you will get 1 minus V naught square by V in into TS by L. Are my calculations correct? Just cross. I think it is V naught. So 1
correct.
minus, so there will be this V naught into 1 minus V naught by V in into TS by L. So now if this is my delta IL. So if V in increases, so I want to see whether they are directly proportional or indirectly proportional. If V in increases, this fraction value decreases and the overall value increases. So V in and delta IL are directly proportional, right?
Yes, sir.
So that says inductor current ripple increases with the input voltage. Now coming back to the constant on time. Constant on time, again, we can directly go so that keep. So there are 2 minutes left. So if this meeting ends, then quickly join so we can continue this discussion. So yeah, so I'll go back to slide number 35. Slide number 35, switching frequency, say on time is fixed. Switching frequency is indirectly proportional to V in, right? Constant on time.
Yeah.
And off time it is directly
Inversely.
proportional. Yes. So on time it is inversely proportional. So I'll change the color, use red color. So constant on time inversely proportional means the first part. And we have seen that constant on time. So V in minus this can, there is less than a minute. If this meeting ends, kindly join. V in minus V naught into T on by L. I can write delta IL, right? So T on is constant, V naught is constant. So this is also increasing with the input voltage. Isn't it? Yeah. Now we know constant off time, it is the other way, which means frequency decreases because it is directly proportional. Now what about the ripple in constant off? I think this meeting will end. Kindly join quickly so we can continue our
It's
discussion.
reverse, right, sir? Because
It is?
it is reverse of on time.
Is it so? Shankar is saying
Yes,
ripple
it will
will be
become-
same, or Shankar is saying ripple will be constant. So which one is it? Yeah. So constant off time. So I can say V naught into T off by L is delta IL. Do you agree? Hello. Hello.
Yes, sir.
Yes.
Yes,
So V
yes.
naught is constant. T off is
These are
constant.
same only.
Yes. So it will
Okay.
be independent of the input voltage, which we have observed here. So this is the relation between them. And just to like show you, I'll quickly go back to that slide and I'll show. So I'll go to 35 slide and then I'll go to this slide. So in this slide, this is for constant off time, as you see. As input voltage is reduced, we have seen that ripple is remains same. Because of this equation, we said that delta L is independent of V. So that is the one advantage of constant off time, you can say. And delta L is not dependent on V input, and only the frequency is dependent, and the frequency relation is frequency is proportional to V in. So if it decreases, V in also decreases. So with this, we'll conclude our session here. So if you have any questions, you can ask, or if you want me to summarize what you have discussed, then I can discuss also.
Sir,
Yeah.
sir, in the slide number 10,
Slide number 10.
there is a overshoot of output voltage also.
Okay,
when
let me go back. Slide number 10, right?
Yes.
Let me do this. Slide number 10. This one or this one? This one, right? Or which one?
Sorry, 9. The 9, sir. Yeah.
Okay, yeah.
Slide number 9. Sir,
Yeah.
in the low transient,
Mm-hmm.
the output voltage seems to be, there is a overshoot here.
Yes. You
Sir,
are right. Continue.
well, sir.
Continue.
Yes, sir. Sir, here again the inductor can't able to respond to this
Yes.
fastly.
Yes.
So because of that, it will continue charging capacitor.
Yes, you are exactly right.
So, sir, actually here the load is actually reducing, right, sir?
Yes. So I'll
Load
go
current
back.
is reducing, resistance is increasing. Okay.
So I'll come back to this same slide. So now what happened is, you are right. Good that you have noticed it. So when output current is increased, inductor cannot supply it, and capacitor is supplying, because of which there is a voltage drop. Now what happens is, say this is connected, so high current is flowing, and now I have disconnected it. So current, there is a step down. So inductor current is at high current, and output says I don't want high current, I'll only operate at low current. So where will it go? It will go into the capacitor. So capacitor will take that current immediately, because inductor cannot have a step function, because it is inductor should be smooth and it also has dynamics. So capacitor will take. So now what will happen? Capacitor is drawing current, right? Previously it was supplying current, and there is a resistive drop at this RC, because of which there is a voltage dip. Now what happens is, capacitor is taking that current, because of which there will be overshoot, because capacitor has taken that charge. Now that extra charge that capacitor has taken, when this switch is closed, capacitor will slowly charge inductor current, and then capacitor will lose its current. Also inductor will try to like reduce its current. Accordingly it will happen, and because of which there is an undershoot. Sorry, there is an overshoot, because that capacitor is taking this extra charge. And that extra charge it will use to, so whenever these are conducted, so capacitor has more charge, so inductor will try to discharge, and accordingly that inductor current will come down.
Okay, until the inductor takes over, the capacitance will take the charge, and again it will dissipate through the inductor to the load.
Yes. So the same thing here, inductor takes some time to deliver that power. So capacitor will deliver that power, and there is an undershoot. Here inductor will take some time to absorb that power. So capacitor absorbs that power, and there is an overshoot.
Okay. Sir, when sir, basically, what we talk about stability
Yes.
in all these facts. Sir, suppose we are saying the system is when D is less than 0.5, it is stable. So, sir, basically we are saying when D is maintained less than 0.5, even though the input voltage disturbance is there or the load disturbance is there, it will come to the both the input voltage and output current will come
Yes.
back to the pre-disturbance value.
Yes, like it will stabilize at some say if it is only disturbance, then it will come to the previous value. But if it is a new steady state, then it will go to the new steady state.
Okay. Okay. When it is greater than, so that is what that Z less than 1 also says, right, sir?
That is what
when
that D.
D less than 0.5.
So that is the condition that it has to satisfy so that the Z eigenvalues will lie inside the unit circle, which means the system is stable.
Okay.
So, sir, in adaptive on time, ripple voltage is constant if I peak is constant. Shankar, no, let me go back to that. Yes, yeah, sorry, you are right, Shankar. So if I peak is constant, then delta V naught is also constant. Yeah, you are right. Sorry. So if I peak is constant, L is constant, V naught is constant, C is constant. So it is constant. Yeah. Okay. Yeah. Thanks for pointing this out. You are right. So I think if
Did you said the other way, sir?
No, like adaptive on time, we are maintaining the I peak. So we are maintaining the I peak and accordingly adapting, changing the on time. And when we substituted, we got this expression delta V naught is equals to L into I peak square. So delta V naught is the effect and this is the cause. So we are, our main motive is we are maintaining I peak, and if I peak is maintained, we are checking what is delta V naught. So now from that expression, we got that delta V naught is dependent on I peak, but since we are maintaining I peak constant, also L, C, V naught are constant. So my delta V naught will also be constant. But delta V naught is constant because I peak is constant. If you see here, I peak is not constant. And here it depends on V in, V naught, T on. So if V in changes, delta V naught changes. So delta V naught is constant for the reason
is in
I peak
constant
is
on
constant.
time.
Yes. Not constant on time, adaptive on time.
Yeah, this is in adaptive on time.
Yes.
So
even if you consider
this
constant
V naught will
on
change.
time, even if
V
V
naught
naught
will
is
change in
constant,
on.
and it depends on V in. So if V in changes, delta V naught changes. Here V naught is constant because we are regulating at V naught, and I peak is also constant, LC are also constant. But here it has dependency on V in, which is not expected to be constant always. There might be fluctuations. So accordingly, delta V naught changes. Understood?
Yes, sir. Basically, in constant on time, delta V naught will bound to change.
Yes.
Whereas in the adaptive on time, we are making it to be equal by through I peak.
Yes. So I peak we are making it constant, and we have seen that delta V naught is also constant because it is proportional to I peak square, and it is not having the V dependency also.
Okay. Yes.
Okay. So if you do not have any questions, let me summarize. We have discussed about. Thanks. Okay, we have discussed about fixed frequency digital voltage mode control and mixed signal current mode control. Then we have moved on to the voltage based constant on time, where we have seen top down design methodology, Verilog HDL experiment results. Then we dived into constant on time current mode control, as well as constant off time current mode control. So these are variable frequency mixed signal current mode control techniques, mainly the constant on time, constant off time, where we have seen some hardware results. Also the dependency of switching frequency and inductor current ripple on input voltage. And then we have seen a comparative study between fixed frequency, constant on time, constant off time, how switching frequency is related to V. We have derived some mathematical expression which explains the reason why it is dependent, switching frequency is dependent with the input voltage. Then we have seen a quick summary of light load architectures, and then we discussed the adapt on time, the control architecture, and how the Verilog implementation. We have seen only the FPGA implementation, which means the block diagram, but we have not gone into the Verilog STL because it is quite similar to voltage-based constant on time, which we have discussed. So that's why we did not go into the details of that. And in the end, we have solved few problems. The first problem being on adapt on time, where we have discussed how to get the on time, provided that input output inductance and peak are given, and in the sub part we have got the capacitance value provided output voltage ripple is 1%. And in the second part we have seen how constant on time, constant off time, fixed frequency, their frequencies are related with the input voltage, and how their frequencies are related with the input voltage, as well as how their inductor current ripple are related with the input voltage. So that is all about this session. Yeah.
Sir, all the images that you have shown from the hardware.
Those are already there in the like lectures that SAR has.
No, sir. No, those are taken from the CRO in the JPEG format, right?
Yes, yes. So if I go back here, there is a pen drive here, so it is saved in this pen drive.
Sir, but will access also will be there, sir, if you take like this?
Yes, like it will be saved in the JPEG, and then we can access. Like what exactly do you mean by that?
No, not axis. This vertical and horizontal axis.
No, axis will not be there. Whatever we have shown.
Okay. Yeah, it is not there, sir.
So it will not be there. So it will come something like this. These dots, grids will be there, and this measurement and other details will be there, but not the axis. Okay, this we can view in the paint itself, right, sir? This we just can view copy in and for example, paint. You can view it anywhere. This is just a picture. So what you can do with the other pictures editing, the same thing you can do it here also. Okay, then I think you got benefited somewhat from this session, and I'm happy that you are asking very good questions, that you are going through SARS lecture, and this session is beneficial to all of you. And I have seen that you're also going through my lectures. Yeah, hope this session is also helpful. And if you do not have any further questions, we can end this session. Let me stop sharing.
Thank you very much, sir.
Okay, then. Bye. Good night. Thank you.
Good night, sir. Bye. Thank you.